Great.
So our first speaker is Simon Davidmann of Impress Software. He's the founder and CEO. His topic today is software verification for low-power safety-critical systems. Simon has been working on simulators and EDA products since 1978. He's founder and CEO of Impress, an initiator of the open virtual platforms. Prior to founding Impress, Simon was a VP in Synopsys following the successful acquisition of Co-Design Automation. He's developer of System Verilog. Before that, he was an executive with European GM. Simon was one of the original developers of high-low logic simulation system, co-authored the definitive book on System Verilog, and is a visiting professor of digital systems at Queen Mary, University of London. And I hand over to Simon now. Just a reminder, Simon, you've got 20 minutes, please. Thank you.
Yeah, that's fine. And you can hear me okay, Mike, can you? Hello, Mike, can you hear me okay?
Yes, please.
Yes, you can hear me. Okay, great. What I'm going to talk about today is software verification for low power and safety critical systems. If we take the title, what I'm going to do is really split it up into two things: software verification for systems, and then talk about low power safety critical stuff. So first thing is really about software verification. And really, there's several things I want to talk about there for software verification. I want to talk about the way that the designs are changing, the requirements are changing, the issues facing software developers in the embedded world are changing, and then how simulation and virtual platforms and advanced tools can help that. If we look at a modern chip, this is a Renesas one in the automotive space, the chip, quite sophisticated, but it has many different processor cores in it. There may be SMP, symmetrical processing cores. It may have asymmetrical cores in there. It may have hardware accelerators in there, which really are processors as well. So you get an awful lot of processing elements going on. And if we just think of even just the main application processor, and I don't expect you to see the detail of all these slides. You can have a look at the video of the presentation later and see the detail. But when you've got an application processor running something like Linux, there's an awful lot of software running, and then you've got all the libraries on top of it, and the application frameworks and things like Android and things on top, a lot of complex software, and it goes all the way from the complex hardware-dependent software all the way up to the applications. And software verification is very complex because of these issues of the SMP, the AMP, the shared memory, the accelerators, external peripherals, which are going to be processors as well, and often you bring in libraries from other people, so it can be very, very complex in there. And then there's all these other issues related to the embedded software. Just for embedded software, you've got the schedule. Everybody wants things done sooner, better quality. You can't afford to have recalls of the product if something goes wrong with it. You need more and more functionality. It needs to run faster, take less power. Has to have safety and security associated with it, and predictability. And actually, there's more and more complexity. So it becomes much harder. It's hard to build a chip, but it's very hard to get software to run on it as well. And to get software to work, traditionally, people have used hardware-based development environments, where you get a board, you get a prototype of it, you get some form of JTAG-based pod and trace in it. But there are several issues with hardware-based development. There's the limited availability of it. You maybe only have one or two of these boards. They might not be in the right place in the world for where your development is. They might not be when you want them. If you want to start software today, the board might be another 3 months away. You might have an FPGA prototype, an emulation of it. Often that will run very differently from the real hardware. It might not have all the different pieces of hardware in it. It might be too slow. It might not be able to do all the right scenarios in there. And even if you do have hardware, it's often very hard to control it. It's very hard to see what's going on inside it. You imagine you've got 10 or 12 different processors interacting in a modern complex chip. How do you control them and get them into the right states? How do you see what's actually going on inside them as well? So it's a real challenge. And the way people get around these things is they modify the software, they add printfs in it, they have debug versions of the kernels in there, they add instrumentation for analysis in there, and they even use different tool chains and different libraries in there. And of course, the moment you start modifying things, you don't end up with the same behavior that you get with the original, the clean source code. So those are all challenges related to the hardware-based methodology. So what we're seeing is people are moving to the adoption of simulation or virtual platforms. And these aren't to replace the current methodology with hardware. Current methodology with hardware, it's proven, it works, but it has limitations. And we think the amount of complexity there, the hardware-based methodologies are at a breaking point. And a virtual platform or simulation-based methodology can augment that and help that. It delivers better things in terms of controllability, visibility, repeatability, and actually automation as well. And they're a complementary technology. They are not to replace it. And they can be used in exactly the same way. You can have the hardware, or you can use a virtual platform or a simulator in there. But also, there are advantages with virtual platform-based software development. You can create a model way before you can actually get the real hardware. So you get much earlier system availability. You're not limited to just having one or two of them. You can have them accessed for the entire team. You can run the real binaries. You're not limited with simulation to maybe running just on your PC with your x86 if you're developing for an ARM or a MIPS. You can actually run the real binary executables, even though you've got an x86 PC in front of you. They can be very fast, in fact, many times faster than embedded systems sometimes. You've got full controllability, and you actually can model all of the environment as well. So you've got access to all the internal stuff, but also the external stuff. So you can actually put the design into different corner cases. You can actually force it to the design and the software to get into the situations where errors can occur. So you can actually track them down and trace them. And you get, as I said, full visibility in it, so that you can actually and see what is going on in a much easier way than you can if you've got real hardware. And if you're in an environment where you're trying to adopt more modern software practices for verification, like continuous integration and or test automation or a lot of regression testing, a virtual platform can be very useful there, because you can have many of them and you can replicate it easily. If you've got hardware, it's very hard to test. If you've got thousands of tests you want to run in different configurations, it's very hard to actually do that and interact. Whereas if you've got a software-based methodology using virtual platform, it's very easy just to run thousands of different runs, maybe all slightly different configured. So using a virtual platform really makes it a lot easier to adopt technologies and methodologies like continuous integration. So yes, you have to build a virtual platform, and I'm not going to go into too much details of this, but you have to build models of the different components or get them from a library like OVP where there's 300-400 different components available. You may have to model your own parts of the IP that's for your specific device, but you can connect them up. You can model what you need to get the simulation to work, and can get the virtual platform to simulate. And when you get it to simulate, simulation is just the beginning. Here's an example of the Imperius tool architecture, and on the left you can see the virtual platform, which will have the application software running on it. On the far left of it, there's actually, you can see there's a test bench. In the hardware world, we had test benches, and also now in the development for software development for using virtual platforms, we can have a test bench as well. So you run your application on your virtual platform with a test bench on your simulator. And then in the Imperius architecture, we have these other technologies off to the right. We have what we call a CPU helper. So this is a technology which understands the specific processor that you've got. We have OS helpers, which understands the software, the operating system that's running. And then we have a collection of what we call VAP tools for verification, analysis, and profiling tools. And then we have a multi-core debugger, which is based around the Eclipse IDE around it as well. So there's a variety of other tools, more than just the simulator, that you can use. So here, what I thought I would do is just give you a little example and show you simple simulation running. So here we have a processor and memory And I'm just going to click a button here, which is going to launch up the simulator. The window will pop up, and this is the simulator running the dry stones benchmark. Very simple, so it's just a processor and memory, and it's just running through the dry stones. So here we can see that it's just finished. It ran some 9.3 billion instructions and ran just under ran 875 million instructions a second, just under 1 billion instructions a second on a Warrior class MIPS processor. And this is on my regular PC, actually, with webinar software and everything running. So it's really quite fast. If we want to see how absolutely fast it can run, I'm now doing another run, and this is what we call our peak speed benchmark to see how fast this model can run. So on my laptop here, 3.5 billion instructions a second. So you can see, 3.5 gigahertz effectively on my laptop, running a MIPS processor again there. So these simulators can be very fast, and not only can they do sort of simple things like ISS, where you're just running your program, but you can run the full system and have a full OS is running. And here's an example here with an ARM platform which has a dual core Cortex A57 with a quad core Cortex A53. So this is their ARM V8 64-bit, and I click the button, I'm going to simulate that. So this is it booting Linux. We've got a console window off on the left. You'll see the text coming up. So this is the console coming to life, Linux, SMP Linux running. And you can see it doesn't take that long to get to the prompt. I'm at the prompt. I can then log in. I can then interact with it. I've got several example benchmarks here. And actually, I could run dry stones on this as well. So I'm running within an ARM. If I and shut it down, we can see we ran some 4.5 billion instructions there. Most of the processors actually aren't doing anything. There'll be a couple of them that actually are doing quite a lot. And it ran some 4.5 billion instructions there. And, so that's basic simulation. But as I said, we have these sort of OS tools. We have something called an OS trace, and I'm turning that on now. And here, before we get console output, we start to see on the left here, we're intercepting the print K messages. So way before we've got anything in the console, we're actually seeing how the OS is running, the scheduler switching, and that sort of stuff. So that by the time that the prompt comes up, we've actually can understand a lot about how the software is running. And this is simple just to help in porting, and now we can see the console starting to come to life there, even though we've had a lot of output at that point in time. And just the third example I wanted to show you is so you can actually see something else. One of the technologies we've got is the ability to trace activity in the processes. And if you're trying to analyze how processes are running, we can actually trace their operation and everything. So I'm just going to stop this. Now we've got to the prompt, and we can trace out. And here I'm using I traced out to. So this is the utilization of the different processes that we're running in that. So we can actually see, if you can see that, it's a bit hard on the screen, I think, with the black with green, but we can see basically traces of the utilization. We can analyze what's going on. So this is from a sort of a design point of view. And so there are many tools that you can have with simulation. It's not just simple, it runs. You can actually trace, sure, you can get coverage, again, non-intrusively. You can get profiling, you get memory analysis. You can get OS-aware technologies like the seeing how the operating system is running and tracing, all at the flick of a switch with the tools, non-intrusively without any changes. And using simulation and virtual platforms is a modern way to develop software. And of course, when it comes to embedded software, if you're using continuous integration or test automation or regression testing, which is what people should be using for embedded systems, then virtual platforms actually become an essential part of it. So that was a little bit about simulation helping to develop software and understand it and to verify it. Let's talk a little bit now about the low power and safety critical. Well, in Paris, we've been collaborating with universities for years. We have 100 universities or so using our technology. We've been working with several, including a European project, on several projects around the use of simulation for software performance analysis using timing analysis, power analysis for software, and also with fault simulation for fault tolerance. So using instruction-accurate simulation for software verification to see how you can comply with standards like ISO 26262 with fault simulation. I'll talk a little bit about that. So just briefly, a little bit about timing analysis. Again, I mentioned about the simulator, how we have this ability to non-intrusively analyze what's going on. Well, we've built some technology which watches the instruction streams, how they're accessing memory, and how they're using other resources in the processor. And from that, we can do a timing estimator, which is just loaded on, again, non-intrusively, and it takes into account the instructions, branches, sequences, and memories. And here's an example around a Cortex-M4. So this is, again, using an instruction-accurate simulator. It's getting, you know, average sort of 8%, and under 10% error compared to the actual measurement of the, in this case, the performance counters in the processor. So this is estimating the timing in there using an instruction-accurate simulator, and it runs still at 500 million instructions a second. So it's very fast to get detailed timing analysis. In terms of power, we've been dealing with, we're part of a European consortium who've been developing something to do with safety and power. And it's really to try and, it's related to people in the aerospace industries, in the transport industries are involved in the project to try and help develop technologies around safety and power in embedded systems. They chose to use the Xilinx Zinc virtual Zinc technology and boards with it as a sort of a prototyping vehicle, and we're involved as Empirus by providing a virtual platform. So we have modeled the processing system, and then you can layer into it the programmable logic, so you can have different configurations you can add to it. One of the partners involved in it is an organization called Fentis in Spain, and they have something called Stratum, which is a hypervisor. And what a hypervisor does is it allows you to put software in different silos or compartments where they can't interact with each other. And that's one of the things that the project is working on in terms of safety, is seeing how safety can be helped by having things in different silos so they can't interact and access things that they shouldn't have. So one of the partners is involved very much with the hypervisor. So that's all running on the virtual platform. Another one is the power modeling, how they can model power. And without going into too much detail, by using the Empirus intercept technology, they built a power model that sits there and looks at the processor and the way that the simulation is running, and has a model of the platform and different power formulas. And they've done they've done a lot of analysis. So as the simulation's running, they've built this power model so you can understand how the software is affecting the power, so that you can try and tune the software related to its power usage. And what they get out of their simulations is actually some traces of the power during simulation, how the software is affecting that. And then they built a power sensor so they can put that back in the system, and it can allow them to have the software be controlling the power, and the power being reduced. So again, that's using simulation for that. And the last thing I want to talk about in the last few minutes, talk about fault simulation. When it comes to things like 26262, there's a requirement that the software, you have to demonstrate that the software, the system is reliable under the presence of certain faults, as it's tolerant to certain fault injections. And in the hardware world, fault simulation was used to show that hardware would be manufactured fault-free. Well, with virtual platforms, we can use fault simulation to show that software is reliable under the presence of faults for things like 26262 standard. And if we look at the fault simulation just briefly, there's really 4 stages to it. You need to do a simulation run to gather some sort of what's called golden data to say this is how the system should be running. Then you have technology to introspect the system and create fault lists and work out, okay, maybe there's going to be single event upsets, or maybe it's going to be stuck faults or whatever in there where the registers are broken or something like that, and create a fault dictionary. Then there's a lot of simulation runs where the system is run with the fault injected in it. Fault dictionary is and then there's analysis and reporting. And this is a technology that's being currently developed based around instruction accurate simulators. And the results are actually very interesting. And this is an example done with the single core, dual core, quad core Cortex A9s with the 8,000 faults generated. And it shows how tolerant the system was to these different faults. And there are actually at the top, there are 5 classic categorizations of the runs that were presented and developed about 5-6 years ago by someone called Cho, which basically says that these, did the fault cause the system to hang? Did the fault cause the system to terminate? Did the output detect it? Did the fault disappear? And it's this type of analysis that can actually show that a system is tolerant to the presence of faults. So really, in the last 15-20 minutes, I've just given you a summary of how virtual platforms and simulation is really helping in the software world and to provide complementary technology to hardware-based testing to try and help in developing better quality software. And of course, with virtual platforms, you can use full production binaries, including the hypervisors and hardware virtualization and everything, which is very important. And on top of just functional correctness, people are starting to get more involved in trying to understand how software is affecting the timing and the power, and people want to do that sort of analysis. And so virtual platforms are becoming essential to the modern embedded software development technologies. So with that, Mike, I'm done in my 20 minutes.
And thank you for finishing on time, Simon. We'll just go to see if there's any questions. Any questions from Bristol? Any questions from Cambridge or France, sir?
No questions from Cambridge. None from Cambridge.
No.
Grenoble?
Was that no questions from Cambridge? Okay. Thank you, Simon. Thank you very much. Thank you.
Thank you very much.